Okay, so welcome to Weathering Sediments and Soils lecture. So this lecture is for spring 2025 GEO 1010 with Dr. Toke. And so I'm at the Utah Quaternary Fault Parameters Working Group this Monday, and so this recording takes place of our usual lecture. So if you have any questions, please reach out via email. Otherwise, I'll be available on Wednesday during my usual office hours between 2:30 and 3:30. Okay, so so weathering sediments and soils. So sediments are all the loose stuff of rock, like fragments of rocks and minerals, shells, shell fragments, and mineral crystals that might have precipitated out of water, kind of loosely available on the Earth's surface, moving around via processes such as, you know, rivers, streams, wind, etc. And sediment is produced by breaking down rock through weathering. Um, if sediment is moved, then we say it's been eroded. But if it's just weathered and loosened, that's something else. So we'll have to always remember the difference between weathering and erosion in this class. And it's important to remember then that we can take bedrock, that hard rock underneath, and form a soil out of it. And you don't have to move that material to make it not rock anymore, just turn it into soil. But you can also, like shown in this picture, you can turn this unconsolidated sediment into soil, and that might have moved prior to weathering. Okay. Okay, so let's go forward. So physical and chemical weathering. So this is breaking down hard rock that might have formed from some past geologic process into kind of its components. And this is done both physically and chemically. And they work together to act rather quickly, geologically speaking, to break down into loose sediment fragments. Okay, so yeah, physical weathering is kind of the actual disaggregation along grain and mineral boundaries, pulling things apart or breaking things. Um, Whereas the chemical weathering is more acting on minerals to change their composition or disaggregate them due to things like dissolution, dissolving in water. So either through alteration or through dissolution is more chemical. And so they work together because to do chemical weathering, you need access to the mineral surfaces. And with physical weathering, you're cracking the rock up and exposing more of those surfaces. If you were to put a couple cracks in, you increase the surface area immensely. So like we have a surface area here of a cube, but if we put in cracks in two different directions, we double that surface area. And then we add some more cracks in different directions, and we get even more area for chemical weathering to take place on. Okay, so what is physical weathering? Another way to say it is that it's mechanical weathering, breaking the rocks into unconnected clasts of variable sizes. The processes can include things like kind of pressure jointing, um, something called frost wedging, root wedging. So these are things that happen towards the Earth's surface with the freeze-thaw cycles and plants wedging their way into maybe joints and prying things open more. And even just thermal expansion that happens with the day, night, and seasonal heatings on the surface of the Earth with these rocks. So we can see some people rock climbing and they're utilizing these pre-existing perhaps joints or cracks in the rock to do their climbing. But ultimately, yeah, we're breaking that rock down into smaller pieces. Okay, so what are those pieces called? So big things like this, we're doing bouldering. Those are boulders. They have a technical classification. They're bigger than 256 millimeters. So that's about 25 centimeters or a quarter of a meter. So a boulder is something that's about the size a foot in diameter, you will say, or a little less. Um, I think of it as a boulder is something that you would need two hands to pick up. A cobble ranges between 64 millimeters and that boulder. And so these things are things that you can hold in one hand, like we see here. This would be a cobble. Pebbles you can hold between a couple of fingers, 2 millimeters to 64 millimeters. Sand, you can see the individual pieces in your hand usually. You definitely feel them, but it's hard to hold just one sand grain because they're so small, between 1/16 and 2 millimeters. Silt, we can sense its granularity. Uh, Sometimes when it's not very easy to sense it in your hand, it might feel pretty smooth. Um, but if you like put it against your fingernail, you might feel that it's gritty, or against your tooth. Whereas mud or clay, it's going to be really small, less than 102, 1/256th of a millimeter. It's really hard to sense that granularity. It tends to be that it's formed of minerals that are called clays, and these are sheet silicates, and they also have this property of um, where they kind of like to stick together. Okay. And so they have this plasticity of holding together. You can form ribbons and things like that with them. And so we can figure out if something's clay versus silt based upon the way it can be manipulated in our hand with a little addition of water. Silt won't hold together and form these ribbons with the water. It doesn't have plasticity. But yeah, so those are the different classed sizes after we physically weather rock. Okay, so physical weathering. Joints are natural cracks formed in rocks due to the expansion of a rock as it is brought up to the Earth's surface or exhumed. And as it's coming towards the Earth's surface, it is expanding because it has less pressure on it. It's also cooling, which causes contraction. And so together, these processes of expansion and contraction crack the rock up. You get different types of joints. So some joints are formed perpendicular to the Earth's surface, kind of like cracks going vertically oriented, and others are cracks that are kind of parallel to the Earth's surface. And some famous examples of this kind of parallel to the Earth's surface cracking is called exfoliation joints. This is commonly seen along like granite plutons. If we were to drill down into the granite, we might see that there's kind of these cracks parallel to the Earth's surface as that rock is expanding, coming towards the Earth's surface. And the heating and thawing as it gets towards the Earth's surface is going to enhance those cracks weakness, and eventually it'll peel off or exfoliate like skin cells coming off of you. But in this case, it's rock layers coming off the Earth's surface, popping off. Okay, when we have joints and cracks, we can then act on them near the Earth's surface and do some more physical weathering. So freeze thaw cycles, when you get a little bit of water in the crack, is important because water expands about 9% when frozen, and that force pushes against the rock. And so that can expand those cracks and help them grow, eventually pop off. Same thing with roots. As the root gets established in one of these cracks and joints, and soil gets in there, water is held, the root and the tree can grow, it gets wider, it pushes it apart, root wedging. And that can result also in eventually the tree will die and fall over. And then sometimes the roots kind of kick up. That's called, you know, basically it's just like the roots are kicking over the soil, right? And so tree throw. Okay, salt wedging. This is also referred to as a physical weathering process, which is a little weird because it's obviously partially chemical. Uh, so this is a picture of something called taphony. You may have seen this in some of the rocks, especially in the sandstones of the Colorado Plateau here in Utah. This kind of honeycomb weathering pattern. This is common in arid climates and also coastal areas. And what's going on is that salt is kind of precipitating on the surface of the rocks. Um, and also dissolving, right, when water falls there, and precipitating, dissolving, getting in between individual mineral grains, forming and popping off individual mineral grains from the rock, forming holes. Once you get these holes, they kind of collect, and um, the process can kind of collect in that area and kind of self-sustain it, and so you get more salt wedging potentially. And it's probably also interacting with other forms of mechanical weathering, such as thermal expansion and animal activity, which might then enhance this weathering process and and kind of popping this sand grains off uh, and forming this weird honeycomb taphony pattern. Um, yeah, so actually, people still are studying exactly how this occurs. It probably varies a little bit from locality to locality, but it is a form of physical weathering with a chemical mediating process. Dissolution is simply dissolving uh, elements from the surface of a mineral in water, thereby taking away matter from that mineral. Um, and then you'll translocate it, you'll move it away. So that would also be a little bit of erosion. But dissolution is taking it off, right? And then you can potentially precipitate it out and form a um, sedimentary mineral somewhere else. But um, yeah, it's a pretty common process. We think of it all the time happening, especially when we have caves. Um, or what we see here, where limestone is forming what's called a karst landscape, where all the little cracks and joints are weathering, preferentially because water is seeping through them and doing dissolving. Um, uh, Calcium carbonate, like we find in limestone or calcite, is a really easily to dissolve mineral. Uh, Even things that we think of as not easy to dissolve do dissolve. So quartz, the stuff that is, you know, basically everywhere in rocks and minerals on the Earth's surface does dissolve in water. It gets saturated at parts per, I think it was parts per million or parts per billion. So it doesn't dissolve a lot, but it will dissolve. Oxidation and reduction reactions occur on the surface of minerals as well. Um, and this is simply just where elements lose and gain electrons across that surface and combine with oxygen. So this is common in iron-bearing minerals and forming oxide minerals. Basically, you're taking silicate minerals and forming oxides and clays and things. And so this occurs in with along with some other chemical processes such as hydrolysis. And basically, this process is super important, or these set of processes, to take our rock forming minerals, the silicates, and weather them down to what we find sitting in soils, which are clays, quartz, and oxides. Okay, a couple more points. So differential weathering. So weathering occurs mostly at the edges and exposed surfaces of rocks and minerals. That makes sense. But actually, in the corners, it'll weather faster than on the flat surface of a, say, a cubic mineral. And so it'll kind of round things with time. And so the rounding of rocks into boulders at the Earth's surface is a natural function of the rate of weathering, which is different on those edges. Okay, uh, there's differential weathering that happens because of differences in strength of minerals and rocks. So here we're seeing this kind of sawtooth pattern in a spire sticking out of the ground of different layers of rock, where we have weak shales and strong sandstone. So the shale is weathering faster and we can see it's being eroded out after it's weathered and leaving down this kind of sawtooth pattern. Okay, so what is soil? Some of you might say it's dirt. Here's my definition. So soil is a mantle of physically and chemically altered sediment, rock, and organic matter that develops due to weathering, including biological activity and other disturbances at the Earth's surface. Because soils are important to both the rock cycle and ecosystems, the zone of soils is also sometimes referred to as the critical zone on the Earth's surface. And that basically just means, right, these soils are critical to both kind of mediating chemical, biological processes between the lithosphere, the solid rocky Earth, the atmosphere, and the biosphere. And so it's critical to life on Earth. Okay, so here's another way to define soil, real simple. Unconsolidated remains of altered rock, plus the addition of organic constituents and other stuff from the Earth's surface. So on the right, you'll see a picture of some people standing on the Earth's surface. They've dug a soil pit. We can see maybe the top of it has got kind of darkened. That's the addition of organic constituents. And we can see some sediment down here, but we might see some patterns in the sediment of different colors. And that's development of soil horizons in there. And we'll talk about that in a minute. Generally, though, you might think of soil being related to deposition of such things as organic matter on the Earth's surface, but most soil is actually mineral content. And where does mineral content come from? It may be blown in on the wind or deposited by water, but primarily it's actually produced from below. The weathering of the rock underneath is what produces soil. So soil production is from bedrock weathering. So from the bottom. And so whatever we have on the Earth's surface there in terms of soil is primarily coming from the minerals in the rocks below, whatever the parent material was. In the hillsides, it's going to be from rocks. On the valley bottoms, it might have been from a deposit of a flood. But either way, it's soil. Okay, so we alter that parent material or rock and we weather it, and we form soil through basically horizonation, or kind of separating out different mineral compositions into layers or horizons. So these are some images talking about that. On the left, it shows like a tree sitting on grass, and then the roots down below. And so where these roots are is oftentimes associated with what's called leaching. Roots might release a bunch of organic acids to help dissolve and break down some of the mineral products in the soil, so they can take it up maybe for some biological process, but also more water coming from infiltration of rainwater from above might help to percolate and dissolve some of that leached mineral matter down below. But it usually doesn't get, all the way down deep into the earth, just a little bit further down to what's called a zone of accumulation. And so stuff that's been leached moves down due to water and eventually kind of accumulates in this zone of accumulation. And so if we were to look at this in kind of this basic soil diagram here in the middle, we end up getting what we call an A, which is a topsoil horizon, an E, which is a leached horizon, and a B, which is zones of accumulation. So topsoil, transitional leach soils, and subsoils of accumulation on top of whatever the parent weathered bedrock was. And maybe, just maybe, if we're a really biologically productive environment, we might have an O horizon on top of that. Okay. Now, I will say that we don't always see a leached, light-colored E horizon. Sometimes it's just happening kind of through a gradation. So we might just have A on top of B with a little bit of leaching in the B and forming. You can have several different types of B horizons. You could have clays accumulating, oxides, and other things. So here we see a good example of that in a real picture. We have grass, organic matter with topsoil, a leached light-colored transition soil, and then a subsoil where we can see some maybe oxidation colors. Um, and so we've oxidized those minerals and brought them down. Here, the leached section, that transition zone, is actually you've leached out a lot of those silicates as oxides, and you're leaving behind silica, and it's pretty much kind of white gray, and that's why it looks like that. Okay, so soils are classified in several different ways. Soils are classified by geologists and soil scientists in terms of how I've been talking about them. Horizons of leached and accumulated zones of certain chemicals due to rock weathering and biological processes. And this has a whole thing of classification called soil taxonomies, as we see over to the right. So there's 12 soil orders in US's comprehensive soil classification system: alpha sols, andisols, iridosols, entasols, gelisols, histosols, and septosols, mollisols, oxasols, photosols, utasols, and vertisols. And so these are kind of groups or orders, right, that have similar origin, either parent materials or they're happening in similar climates, things like that. For instance, andesol forms in soils with a lot of volcanic ash and materials. So you might find them in like a subduction zone environment. A mollisol forms in subhumid to subarid grasslands. Excuse me. And we actually have a lot of mollisols in Utah. Oxasols only form in tropical environments due to really deeply weathered soils. Okay, so that's soil classification. Engineers talk about soils in something called the Unified Soil Classification System, which actually has nothing to do with the processes of weathering and fully only to do with what is there in terms of mechanical properties. Is it gravel by itself? Is it sand and silt? How does it behave under stress? Okay, so we're not going to talk about engineering soils, but just be aware that that is a different thing. Okay, so here's our classic soil profiles. If we were in class, I would have asked you to kind of describe what you see here and kind of relate it to this. But hopefully everybody's seeing that there's a topsoil here, and maybe there's a leached horizon here with oxides below, and then maybe some different sediment below that. But the point being that we have several horizons of soils in here. These horizons are not flat across. In some cases, you can see maybe where roots have allowed organic matter to get lower down. We can see that the horizon lines are sometimes gradational. So here between this lighter and this more oxidized rusty color, you can maybe see that it goes back and forth and it's not like a straight line. And so that's important to remember. And this, what we see here in terms of the topography of these horizons can have to do with water content, water infiltration, as we see in these roots. And it can also follow patterns of topography on the Earth's surface, although here it's flat across, so we can't really see that. Here are the soils that you find mostly in Utah. We have 5 soil orders in Utah. Of them, the most common are mollisols, grassland soils. We find those throughout the Wasatch Back, like over in Heber and Price and near Park City, these kind of rolling grasslands. We find them some on the Wasatch Front as well. We have iridosols, which are a desert soil. They don't have much water in those environments where iridosols form, and so they accumulate salts in the soil. And salts can include things like calcium carbonate, in addition to like your traditional salts that you might be thinking of. So those are found out in the deserts. And then these light-colored yellow and tan entasols and septosols are super weakly developed young soils. The entasols are really weak, so basically almost no soil development, so super young soils. They're found in like floodplains out in the desert environments or the Colorado Plateau. And the septosols are and also weakly developed, but we're seeing that most of them are located in highlands environments in Utah. They're maybe associated with areas that were recently glaciated, so the soils were plowed over, and they've only been developing for the past 10,000 years or so, not very well developed. The only other type of soil that's super common in Utah is called alpha soils, which happen in areas where there's a strong leaching environment. And so here, this is along the edge of shores like Great Salt Lake, where the water levels goes up and down, and as it does so, it leaches out material from those soils. So here's a picture of a grassland mollisol. These typically have deep A horizons because those grasses have deep roots, which allow us to move organic matter down. There will be B horizon. Generally, there's kind of semi-arid terrains. And so in that B horizon, you might have accumulation of carbonate and maybe clay. Clay is symbolized in this picture as Bt, and the Bk means carbonate. Iridosols have lots of carbonate in the subsoil. That's kind of characteristic of them. And they're interesting because these iridosols can be kind of indicative of time, of the age of geomorphic landscape surfaces and soils themselves. So on the right here, you see this picture of a rock hammer sitting next to what maybe looks like a big bunch of cement, but actually that's carbonate formed in this soil. The river is cut in, and so we can see that. That's probably what we call a stage 4 carbonate. And if you know your kind of stages of soil across the region you're in, so in this case, the desert Southwest, a soil of that order would tell us that we're probably thinking about it or seeing like a 300,000-year-old geomorphic surface, seeing that much carbonate, because it kind of accumulates linearly with time if the climate stays kind of steady. Entasols shown here. As I said, this was a super, basically weakly developed soil. And so all we actually see is C, which is parent material, which in this case is silt, and then A, which is silt blown in from the top. So not much of anything going on here. These soils are not very good for agriculture. They're very poorly developed. They don't have much organic matter. Not very stable. They're quite weak. Inceptisols are better developed than entasols. You find these in these highland soils. They might have a nice dark A horizon with organic matter. They're usually in a more wet environment, higher alpine soils. They'll be on top of like a rubbly parent material, and they might have a little bit of a B horizon development below that A horizon. They tend to be pretty thin in steep landscapes. Again, not great for agriculture, but better than the other one. And here's a picture of that leached alpha sol near the Great Salt Lake. We do have an accumulation of clay in the subsoil, but we can see that kind of the A horizon is not much organic matter, mostly just silt that might have blown in from the wind. And the E horizon is that leached zone, which is just leaving behind whatever couldn't be leached out, more quartz than anything else. And I will say that A horizons, while they're usually associated with organic matter and darkening of the soil, in this desert environment like we live in, dust is another component from the top. It's really a component everywhere around the world. You probably notice all the dust accumulating in your house all the time. It's accumulating all over the Earth's surface as well. And so it's in that topsoil. Okay, so how do we get soils? Well, we already talked about rock weathering. We can also get deposition from dust and organic matter from the top. Okay, so soils are depth dependent. This little bit of graphic we might talk about in class, and it comes up, I think, in your journal. So soil is optimally produced, or rather rocks are best weathered when there's not a ton of soil on top of them, if that makes sense. So if you cover the rock up with a bunch of sediment, then water and biological activity is not able to get to it, and so soil production will go down. So that's what this graph is showing us, right? Soil production goes up as soil depth is less. This is an exponential decline model. So it basically says that you'll get more weathering of rock and more soil production if there's no soil. um, but people have actually realized it's not quite true. Actually, you need a certain amount of soil to form to get the optimal amount of weathering. And this is humped model, okay, of soil production. So you need a little bit of sediment and soil sitting on top of the rock to optimize how much weathering you can do. Why might that be? Well, you can think about it, but a lot of that weathering is going to have to do with water. If there's no loose material there, the water is going to evaporate or run right off. And so it's not going to be there very long to interact with the rock and weather it. But if you have a little bit of thickness, maybe a little bit of plants and things like that, holding that water in place against the rock, it's going to do a lot more weathering. And so that humped model of soil production is probably more true. And so we can see that maybe even reflected in some of these soil forming factors pictures. So this shows where our soils are thickest and thinnest. So the desert regions and the polar deserts have the thinnest soils. Temperate regions have thicker soils. Tropical soils are so thick, you can go down tens of feet into the ground before you get to the weathering horizon with the rock. And so again, it just shows the importance of water interaction time, also with temperature and the rock to do the weathering. If you don't have much soil on top, you just got a bunch of rock, not much water, not much soil depth. What happens in terms of weathering is also dependent upon what's there for minerals, what's being weathered. So some minerals don't like to do much weathering. Think of quartz, and others, maybe the more mafic minerals that we find, weather quite readily and nicely. Steepness is important. So if again, if the rocks are super steep, then maybe the water is not going to be there very long. Yeah, and it's not going to retain the moisture, so it doesn't weather as much. But whereas you're in flat, low-lying areas, water is there, we get thicker soils. And time. So time is important. So the longer that rock has been here, the more weathered it will be. Younger soils tend to be thinner. Okay, so bottom line, what controls soil depth? What it's made of, parent material. The climate. Related to the climate, what vegetation is there? How much time has passed? How steep is the landscape? How much water is there available in the soil? And so soils that we see are linked to their place in the landscape, their climate, the biome, time, and rock type. I will stop this lecture here, and we'll kind of pick up in class talking maybe about that soil production model and this graphic right here, which talks about erosion rate, which is a little bit different than weathering rate, but they're tied together. And so we'll cover this next time in class. All right, I'll see you on Wednesday.